Hello guys, so today we are again looking at this Jane Street real-time market data forecasting competition. So far I have seen couple of notebooks. So people are modeling simply XGBoost, CAT-boost models, and they are not even considering any uh lengthwise data like past data. So mostly they are using only 1 lakh data for the responder 6. So, in order to check that, I was thinking of conducting some statistical test. Uh, okay, let's try to do it. Let's pick EDA 3. I guess I do not have any EDA 3. Okay, so recording pandas and other thing I will be needing. I guess let's start with that only. And yeah, one more thing we observe that the NaN values are very less for the last partition. So let's take this partition only. Let's call it DF path. This is my DF path. Let's do park it. Okay, cool. So the first thing we should look at is whether this responder 6 is actually a stationary time series. Now, what does that stationary means is that the mean and the variance and as well as the autocorrelation, so they are remaining constant with respect to, like, they are not varying too much. So it's a um we call it Dickey Fuller test. Okay, and here we are essentially checking whether the time series data that we are given, that is remaining stationary. Okay, so the null hypothesis says that whatever time series data we have is not stationary. Okay, and it conducts some test, and from which we get a p-value, and if p-value is less than my 0.05, that means our alternative hypothesis is correct, which is this hypothesis. Otherwise it's not a stationary, so it's not a time series problem. Yeah, so let's first do that. Now in order to do that, so there are we have this famous library stats models. I guess this is, we call it augmented Dickey-Fuller test. So I don't know whether I'm importing it correctly, but yeah, let's have a check. Add Fuller, we call it. Mhm. Yeah. Okay. Add fuller. Okay. Cool. Okay. Now, there are around 6 million rows, so we cannot take 6 million rows as it is because it will overload our RAM. So instead, let's take a sample size of, let's say, 10 to the power 6, and let's check it for one symbol. Uh, let's do it for 0. Okay. Then let's load our FDF. So I'll be considering the last uh, data. Now FDF will have 10 to the power 6 rows, and yeah, so 100k it's 100k, right? Yeah, no, 1000k. Yeah, so yeah, 1000k rows, and we will simply check the result of our decay fuller test with respect to our label, which is responder 6. So we can check this. I need to remember what does it gives. You got this. The okay, first value is your p-value. Okay. So you can say something like this. So if result of 1 is less than 0.05, we can print, okay, responder 6 is stationary, which means it has so we can model it as a time series problem. Otherwise, responder 6 is not stationary. Boom. Okay, moment of truth. Let's check whether this competition is a time series problem or not. Okay. It's taking some time. Maybe our sample size is big. That's why it's taking time. But yeah. Okay. So responder 6 is stationary if we consider all the responder 6 value with respect to symbol ID 0. Okay. So I took this sample, and it doesn't mean like if I take the whole population, this result will be different because we have a lot of data. So if we consider a good amount of sample size, then I guess our statistics uh, is good. Cool. So, but this is for symbol ID 0. It will be better if I do this for all the symbol IDs. Okay, so in order to do that, let's decrease this and let's put it here, and let's write a for loop for symbol ID in so we got symbols. Okay, this will list down all the symbols, and then symbol IDs. We want to do this. Okay, and let's put the symbol also. And it will be better if I do this in a data frame. So let's create a data frame. We will create zip values. So rows. Okay. Now this. Let's go as stationary. So symbols verdict. Let's make it here. Stationary. If this, else non-stationary. Okay, and we will append this. Symbol ID and symbol verdict. Okay, cool. And it will be better if we also show the result so that we don't have to wait. So symbol okay. We can further reduce it. 10,000 is also enough. Let's do this. Okay. Okay, so far everyone is stationary, so all of the symbol IDs are time series. If I remember, we have around 38 symbols. Let's check. Oh, okay. Cool. Uh, just a second. Cool. So up till here we can see like all of them are stationaries, which is nice. Cool. So this is indeed a time series problem. Is it recording? It is recording. Okay, cool. So this part is done. Then the next part which should focus on is like if this is a time series problem, so we have this thing, right? So uh, if this is indeed a time series problem, so how much lag we should look, whether this is influencing this or this plus this is influencing this or this. So in order to do that, we can consider some kind of a autocorrelation plot. Now what autocorrelation does is, so it basically checks, so it takes some lags and based on that it simply tells us like what's the correlation of the data captured at t time with respect to the data based on some lag, I being the lag value. Okay, Now let's take a sample first. Okay, we can use the same code here, and we got symbols, this, and we don't need this. If I remember, those are called ACF plots, right? That's this. Yeah, you can see like we have one autocorrelation plot, and there is one partial autocorrelation plot. Now, autocorrelation simply tells us like uh, so we have two things here: autocorrelation and partial autocorrelation. Okay. Now, this first one measures the relationship between a time series and a lagged version of itself. So, as you can see here, so this is plotting. So, with respect to every lag, as you can see, like there is a sinusoidal relationship with the lag values here. Okay. And from this also, we can get a understanding of the seasonal patterns, whether there are any periodicity involved with respect to the patterns observed in the lag data. And yeah, but the most useful one for checking how much lag we need is this partial autocorrelation, because it will do the same thing, but it will give us the cutoff, like what how much lag we should consider. Okay, so from this plot you can see like it has two significant, so lag 1, lag 2, okay, are significant lags, like it has a correlation of 1. Okay, whereas other lags are significant but not up to this much. So for this data set, whatever data set this guy has done, so only 2 lags are sufficient for modeling the label with respect to its like lagged version. Okay, uh let's first do it for one. Okay, and I need the import. Okay, so it's graphics TSA plots. Kaggle suggestions are worst. Partial autocorrelation plot function. Okay. Why? Okay, cool. So we got this and this, and this will be better if we can plot two side by side plots. I don't remember the code. Plot grid. So we will be needing two plots for all the symbol IDs. Okay, and so this will be n cross 2. Okay, we should do this. Let's first try for one plot. We don't need this. Plot ACF, FDF. We need responder 6 and PLT title. Let's call it ACF for responder 6 with symbol ID this. Okay, so this will put it here. And one more thing, this is plot PCAF, partial autocorrelation plot function, and here we will pass again the same thing, responder 6, and we will do the same thing here. Okay, and yeah, I think this should be PACF. Cool. Solid state import. Okay. Have I not imported this? Lib import pipe plot as PLT. It's a good thing to have markdowns so that I can easily navigate. And let's create a markdown here. Loading dataset. Okay, boy, cool. Let's call it stationary or not. Okay, we got this. PCF and ACF and PCF for each symbol ID. Okay, cool. Now this should work. So you can see here. So it has a gradual declination with respect to its lagged versions. Okay, and it has taken up to 40 lags, and we don't see much influential after 20 lag, and there is a gradual declination from 0 to 20. Okay, so we can see like 1 to are little bit significant up to like 75% correlation is there up to 1 2 3 4 5 5 lakhs. Okay, but there is a very high correlation respect to here. So here you can see like the clearly the cutoff here, right? Yeah, the first one being the value being with itself, so 0 lag. Okay, so yeah, that this means like this is up to 4 lakhs. Okay, 75% correlation up to 4 lakhs. And if you look at this thing, partial autocorrelation function, so lag 1 is highly significant and rest of the lags are less significant. So for modeling we can consider this factor, like if we lag our data by one time ID, okay, then that means we will have a good metric for a good feature for predicting the current value. Okay, so we can note it down. So lag 1 has a high correlation. Okay, now this is for symbol ID 0. It's better to see for all the symbols that we have. Okay, now in order to do that I need some code. Actually I forgot how to do like side by side plots. Plots side by side. Okay, so you do this and this. Okay, so you have to mention subplots. Okay, there's a figure here. So let's width I can consider 15 by 15. Okay, and I have 2 columns. I need one column. I need one row, two columns. Yeah, one, two. Okay. Then cat column subplot. This takes rows. Okay, and here you bring in your plot. Okay, so first goes here. Okay, then there is plot counts. I don't know why he is doing this. Simply giving subplot should work, I guess. Okay, I'm showing this. X ticks I don't need, and this I don't need. Okay, and I just need this. Okay, I don't need this. So there should be one, then plot count. Ah, okay, that's why. Okay, let's increase this then. Plot count, and this will be +1. Okay, symbol ID this and this, and yeah, so we can make it enumerate, and this ID, so this will act as a row index, so I don't need you. Bye bye. I have two columns, so I don't need this also. So this goes here, and of this I will put this +1, and yeah, so row index are one base indexing, that's why +1. Okay, column index is this, plot count is this, and there is a plot count +1. Okay, cool. Fingers crossed, should work. And yeah, it didn't work because I have removed this thing. Okay, so it just takes 1 and 2, right? Ah, okay, something is wrong. I don't need you. I made the figure here. I'm doing this. One, two. Oh, okay. So this also two. Still not giving me side by side. Something is wrong. Oh, is it because of this? PACF is coming in the end. Okay. Ah, it's too much iterations. Okay, there is row index. I got 2, 2. Where is my ACF is going? Is your logic? Just this, right? why it is making this much. Okay. Okay, let's quickly check the documentation. Auto plot, multiple subplots, yes. So this add subplot, then okay, you create this axis, you add this subplot to here. Oh, okay, here you are mentioning this. Hmm. I want to do it side by side. Number of columns. If I don't do this, okay. What are those three arguments? It just takes a arcs here. Are they giving any examples? 2, 1, 1. Okay, this is equivalent to this. Hmm. Can we give access here? I can go where the access path. Okay, it takes access. Okay, this is just too much. So okay, I need 1 and 2. Okay, put the size as, I want more width, so 20, and height as, let's say, 6. Okay, and I don't need you. I don't need you. It takes access, right? So access, access 0. Then more thing. So yeah, we should. Okay, one more thing. This doesn't work, right? And this goes as set title, and I can copy this here. Okay, and simply should work. Let's press 1. Cool, nice. Okay, we got this, and cool. So for symbol 0, we have this. Now let's look for all the symbols. Hmm. I guess for all of them, this is kind of identical. So lag 1 being more significant. Okay, we are seeing a little bit of sinusoidal nature for symbol 21. So for all of the plots, I can see like lag 1 is, yeah, so lag 1 is like the cutoff for us. We should not consider more than that. Okay, cool. Okay. Now the next thing we should look at, like, so if we simply plot the correlation plot, we are not seeing any good thing, right? Because here I tried the correlation plot earlier, but I didn't see any pattern from them. Ah, yeah, idiot too. So yeah, none of the features are being correlated with any of the responder. So I guess a better way should be if we can use some statistical method that can predict whether which of the features are better, like have some causality with the uh, responder. Now for that we can consider, this Granger test. Okay, now what does Granger test says that, okay, if your time series is stationary, okay, okay, let's say your y stationary, and you have some excess, okay, which are also like varying with time. Now to check the impact of a xi feature on y, so we can conduct multiple t test and f test, and based on that we can have a p value for this xi. And yeah, same story goes, like if this is less than my 0.05, then this is significant. Okay, we can use this. Otherwise, we should drop that feature. So yeah, let's conduct a Granger causality test. Okay. Now, how does this work is like, so you have some YT, okay, and since this is stationary, so it's getting influenced by, and we saw like it's also autocorrelated. So we can define it something like this. T minus 1, or let's put this as 1 only. So this is lag 1. So some weight for lag 2. Like this, we will be going for some nth lag, and then we have some error term. Okay, because this is how we define a time series. So usually any time series is composed of like trend plus cycles, okay, then seasonality, and plus some errors. Okay, this is how a time series data is usually defined. Okay, so trend being like, if you check this time series only, so there is a trend, like it is always going up. So in stock market data you will also see like there is a trend in the stock value, so either they are always going up, or if you check one part of the data, let's say I consider this part only, so this is something like this, like, so this is also increasing. Okay, now couple of stocks value, you also see like if you consider this, there is a downward movement here, so I can say like the trend is downward. Okay, and seasonality being like, as you can see here, like if I consider this period only, okay, so this pattern is kind of repeated here and somewhere here, so not exactly, okay, but it has some kind of a pattern which is very similar to the past occurrences, so that becomes seasonality. And same goes for cycles, so you have some patterns, so in around, if you fixed a period, it will also always show you that same relative nature of growth and seasonality. Okay, now because of this three things, modeling a time series is kind of hectic, because like when you have some kind of, let's say you are working on a supervised data, okay, so you have data and you have some fixated values, right? So let's consider if you want xy, so for 1 you have 2, for 2 you have, let's say, zero point 0.5, some kind of like this. Okay, let's say usually when you have this kind of data, you can easily fit a model that can predict this values, or you can train a neural network that can predict this values. Okay, but these are not changing with respect to time, these are constant. But in time series, because of this three factors, okay, they are not stay like static, they are kind of dynamic. So that's why forecasting models are kind of very tedious and lots of work are needed, because that's why like nobody can predict the stock value of like future, right? because because of these three factors. And yeah, so once you cancel out these factors, okay, the only thing you need to care about is this error, which you can also call it as a residual. Okay, okay, once you have cancelled out these three factors, so then your data will become some kind of a static, which is like not growing and not showing any trend, and it's not changing with respect to time. Okay, then you can easily model that time series model as a static data set. Okay, but in order to remove all this, you have to do some algorithm. Okay, now this was about the time series, but yeah, let's check which all features are relatively important with respect to our responders. So yeah, we were in Granger causality. This funny name, causality. Okay, now in order to do that, so I guess we also have some kind of let's search for it. Granger causality tests. Yes, this one. Ha. So this is the way. And one more thing is like whenever you are conducting this test, so your data should not have nan values. Now, before we do it, so for this we can consider one set. Okay, let's take symbol or whatever FDF we have. Okay, so this is for symbol ID 29. Let's check for this only. Okay, so we have this. Okay, so first we need to import this. Stat tools. It's better to just copy this. Yeah. Okay. Now we saw that we need a lag of 1, like max lag is significant. Okay. Now this is for this part. Okay. Now what we will try to do is for xi, this test will take a like for this x, it will consider a p and a q. This being that the shortest lag in the data set for this xi and q being the longest lag. Okay, so it will try to check whether yt is better expressed in the form of, so you will have this above term. Okay, yt minus 2 and then this test will put x while expressing y in the form of something like this. Let's say b as like p. Okay, and x t minus p. So we are considering lagged values for x. Okay, and this will go up to some constant, then x t minus q. Now here if you check in y, so we are starting with one lag. Okay, but this test will take this, will consider this p value, some constant it will take. Okay, and from that lag value to a longest lag value it will also predict. Okay, it will put in the expression, and the test will check whether this is better for expressing yt or this is better for expressing yt. Okay, now if this is better, then we will say that xt or whatever xi I have as a feature, that has a significant role in describing y, so we can use that for feature selection. Okay, so this is max lag. Yeah, max lag. Then we need to consider all the features, right? So, and yeah, we should fill all the nan values. Okay, now fdf, so we should fill many, so we should first fill them with forward filling, and we should then fill it with 0. Okay, so what does this mean is like if you have some kind of this one nan 2 3 4 nan. Okay, What forward filling will do is, so it will put 1, 1, 1, 2, 3, 4, 4, 4. So this 4 will go here, this 4 again will go here. So one will come here, one will come here. So it fills in this way, okay? And in our data set, since couple of rows are like in the beginning, they are nan only, okay? So forward filling will not work for, let's say I have some kind of like this. I have an and here, okay? So I do not have any parent to fill them, right? So for this, I'm filling them with 0. So this line basically means that, okay? So what for all the rows which have nan values in the beginning, fill them with 0. And for the rest of the like for rest of the nan values, if they have a parent, fill them with the parent value. So forward filling is that, okay? Now need some kind of cache to store the result. So let's call it danger results. So this will act as my cache. Then for feature in my FDF columns. Okay. Now I don't need to consider date ID and time ID. Okay. Uh, Rest of the things I can consider them as features, and I should also not consider all the responders because they are not available in my test set. Okay, not in. So let's define not required, not considered. Okay, so I don't need date ID, time ID, and yeah, this is one. And I should not consider symbol ID also. Okay, and let's consider weight. Okay, and one more check I need to do is if feature uh, starts with, so now it starts with res. Okay, or this will be better like feature in this, or feature in starts with res for responders. We will not consider that. Okay, or I could have like simply put feature, like if starts with feature, that's also a cool idea, but okay, we can do it in multiple steps. Okay, now for all the feature columns, we will try to do the Granger test. Now, also one thing to consider is that, yeah, first thing being nan should not be there. And second thing is if you have constant columns, by constant columns, what do I mean? Like if a column has like 0 0 0 0 0 0 0 0, like this kind of column, okay, so there is no change or delta, so entropy is pretty less here, okay, so no information gain will happen here. So this test simply will throw you a error. Okay, now in order to avoid that, that's why I'm putting this as a try catch. So constant or static columns should not be considered. Okay, so these two things we should consider. So let's take this ranger causality, let's copy, let's paste. Okay, FDF. So oh, I also need my target column so that I can use it. Responder 6. Then I got my target column here. Okay, and then the feature column I have. Okay, Then I need to put the max lag. So for this, I'm considering max lag as 1, as we saw in the autocorrelation plot. Then I don't need, so verbosity is there, I guess, but by default, I don't know. So let's put it false. I don't need any logs here. Okay. Then I will save it in the cache. Ranges, results, feature. So now let's look at where does it gives the p-value. Okay, it returns a list, a dict. Okay. Let's first run for one and check the result. Uh, pass accept exception as error. So let's put error. Whew. So for this, let's check out what error we will get for features, so that if there is a error in the code logic, then we can easily debug it. Okay, let's try out for one feature. Yeah, I need to check where does the p-value get stored. Okay. So you got this. Yeah, I need this. And this is my max lag. I need, okay, this gives a tuple. I need the first one. And yeah, this is the p-value. Okay, cool. So, yeah, just a second. Yeah, cool. So we have the p-value here. So, I got this test res. So whatever lag value I have given, it will give me with respect to that. And we got f test and the first value, that's the p value. Okay, we got this. Now we should put it in our cache only when we are getting a significant p value. Now p values does not give you like the order of significance, it's just a statistics test. So if any p value is crossing 0.05, that means it's significant, but the magnitude of p value does not describe its impact on the feature. It simply says like, okay, it has an impact. It doesn't say like how much impact it has. Okay, so this, and you can say if p value is less than 0.05, then only I will put it in the cache. Okay, cool. Now this should work. And in the end, I can print out the results. Or it's better to use a data frame. So Granger results. Boom. Yeah, okay, error. So 9, 10, 11, I guess they were like completely nan. That's why this is giving me this error. Now, how's my Granger results looking? Okay. So uh, let's describe the columns as okay, feature, p-value, and data as I need list of zip. Now Granger results. So please go here. Let's make them list, and also Granger results values. Okay, give me my data frame. Object is not iterable. Ah, okay. Use. Cool. So it says 6 and 7 and 64 are very significant with respect to our responder 6 for symbol ID 29. Hmm. Let's try removing this one. Okay, so all of the responders have a very uh so all of them are impacting this uh responder 6. So features 6, 7, 64 only. Interesting. Okay, so from this so we can have an idea like to build a model to figure out all these features, and from that model we will try to figure out feature 6, responder 6. Okay. Whew. Okay, now this is one. Cool. Now one more thing we can try is like actually fitting a simple algorithm just like linear regression uh, over the data set, and let's check out the coefficients of that value, like coefficients of all features when it is trying to predict responder 6, because how linear regression works is like you have some points in the data set and it tries to okay, I guess I have drawn the line earlier. Okay, so if you have data like this, like scatter around, now linear regression will try to fit a line that passes through most of the points. Okay, I guess this is not a good regression line, but yeah, the idea is same, like it will try to fit in a line so that most of the points are very close to the line itself. Okay, so distances from all the points to that line is like minimum. Okay, now for us this is kind of a multivariate problem because there we have lots of features, like we have 79 features. Okay, as well as we have like time ID and date IDs, right? And then we also have this weight thing. Okay, and one more thing is like all the responders. Okay, so let's consider first this 79 features and let's check out. So from this test we have an idea like feature 6, 7, 64 are good. Okay, but this also has some limitation, like so it can happen that so when you have two feet to like here only, yeah, when you have a y and xi, okay, xi being the feature, now Granger test lacks So it has this limitation, like when these two are getting influenced by some third party. Okay, let's call it uh, some, let's say L of I. Okay, okay. So it's something like Xi is getting influenced by Li, and Y is also getting influenced by Li. Okay, but when we are conducting a Granger test on this two, okay, the test will fail. Like it will fail to determine whether Xi has a relationship with Y, because this one is hidden. We don't know that. Okay, so these features are the ones which are like directly impacting Y, but couple of features which have some kind of uh, non-direct effect. Okay, so those will be missed with this test. Okay, but still this is pretty good. Okay, we are getting like features which are like directly impacting our responder 6. But yeah, in order to catch those features, we can try putting a linear regression over responder 6 considering all the features. Okay, and we can check out the coefficients of them. Okay, okay, so let's try fitting. Let's call it linear regression. Okay, uh and I forgot how to linear regression. Okay, sklearn linear regression. So from sklearn linear model, import linear regression. Okay, now one more cool thing about linear regression is that, first thing, it's pretty naive and vanilla, and it's very easy to implement. Okay, and also many statistics tests are conducting linear regression in their underlying mechanism. Okay, but the cool thing about linear regression is that, so like I said, like determining or forecasting time series data is problematic because of these three uh, factors. Okay, but linear regression is one of the popular algorithm which can uh, like learn all this and can help us to figure out the forecasting values. Okay, so linear regression can easily learn these features. Okay, trend, cycle, and seasons. Okay, now one way to look at the problem is that if we have trained a model for linear regression, okay, on the data set, now whatever model predict we are doing, okay, it will capture these three factors, okay, plus this error. Okay, so trend, cycle, and seasons. Okay, and also it will have some error. Okay, now when you are subtracting, let's say this is your ground truth, when you are subtracting this y ground truth with your y pred, you are only leaving out with y residuals. Now this residual is nothing other than this error, which basically means this value is kind of detrended. So we have removed all these three factors and we are only like letting with error. Now this we can easily model with another algorithm. Now why I said linear regression is a very cool algorithm, because linear regression can do this, but if you go with any tree based approach, they cannot do that. Tree based algorithms cannot do that, as well as neural network, because these algorithms are more focused on, like, by neural network I mean like vanilla neural network. Okay, but considering LSTMs and GRUs and even transfer models, they have so since they are black box, so they are somehow figuring out the trend, cycle, and seasons, so they are kind of learning it. But if you consider a simple neural network, then and also tree based algorithm, they cannot learn the trained cycle and seasons. But linear regression kind of algorithm, they can easily figure out the trend, cycle, and seasons. That's why in many companies and many competition, linear regression is standing top of tree based algorithms. Okay, but it's not that you should only focus on linear regression. You should also focus on other algorithms, because the separation of features and weighting a feature more than the other, and some kind of figuring out the non-linear relationship, those things are difficult with linear regression, but they are easily figurable with tree based algorithm. So the idea should be, try to model a linear regression first. Okay, then use the prediction of your linear regression to get the detrended data. Okay, so basically subtracting out your ground truth with wipe red, that's your detrended data. Then try fitting a tree based or neural network, or you can say NN. Okay, now this thing is pretty nice, because once you have detrended data, these are static data, those are not changing with respect to time. Okay, now tree based model and neural network can easily figure out the underlying mechanism and the interactions, which are not capturable with linear regression. So this kind of algorithm is pretty good, and we will call it hybrid approach. So yeah, but let's first check out the coefficients with linear regression for all the features. Now, since the data is huge, so how much we have? FDF, we have 10,000 rows. Yeah, we have 10,000 rows. So let's quickly fit a linear regression. So we have linear regression. So also, since this is the linear algorithm, so it requires us to like standardize the data. Scalar, then we need train test split, model selection for train test split, and yeah, I think we should be good. Okay, have I imported numpy? Let's make this top. Yes, I want to leave. Import numpy as LP. Okay, let's go back to linear regression. We got our linear regression. Let's first instantiate our model. So let's call it our model. So linear regression. Okay, now let's set it to n jobs. So this is pretty necessary, because otherwise it will take a long time to fit the data. So n jobs will help you to like use all the cores that you have. Now if you simply look at how many cores you have, is import os dot cpu count. Okay, so we have 4 cores. Okay, and we want to use 4 cores for computation. So if you don't set it to -1, then it will only use 1 core, and it will take long time, and you are kind of not using the power that you have. So yeah, n jobs is 1. Then the next thing will be, so I have already filled all the nan values, right? FDF is null. Can I do this? This, and where I want to say FDF dot 0 not equal to false, or is okay. I'm really doing some silly things, but yeah, I guess I do not have that. Okay, so all of them are 0, so no null values no null values are there. Okay, now yeah, this is my model. Let's go here. Then let's segregate our data. So we have X. Now what I want to do is X, so let's call feature calls. Okay, now this should include all the features. Okay, so call for call in fdf dot columns, if call dot starts with p. Okay, so and target call is responder 6. Let's check out our feature calls. Okay, we have all the feature calls. Cool. Then the next thing will be make it in a list so that we will have data frame. So here only let's create our scalar. So let's use standard scalar. Okay, and extracting features. So fdf or let's call it features is equal to fdf. So we have extracted all the features, and labels fdf target call. Okay, now we need to scale them, right? So you can see like I have not considered date ID and time ID as features. Okay, we can use them later, but yeah, this exercise is only to check like which features are important for responder 6. So uh features, or let's check feature scaled. Okay, now I simply need to scalar dot fit transform. Okay, so this will fit over the data and transform our features. So yeah, we have this. Then we need to divide our train test split. So get x train, we get x test, then we get x y train, and then we get y test. Let's split. Now let's take feature scaled. Then next thing is labels, and yeah, I need to define my test size. So I have 10,000 rows, so let's consider 0.2 of it, so 2,000 of them. And yeah, so this thing is necessary, so random state 42. Cool. So let's make this, or I can bring this code here. Let's remove this. Let's remove this, and call creating model, and let's call this pre-processing. Okay, now once you have this, I need to fit this, the simplest task in machine learning. Cool. So I need to do training. So LR model fit. I need to do X train and Y train. Okay. Now once I have this, so this will fit. Let's first run this. Okay, that was pretty fast. Okay. Now next thing will be feature importance. Okay. So feature importance. So this is something you can also get with random forest, but yeah, as I told you, tree-based algorithms are not good for learning trends, cycles, and seasons. So that's why we are fitting a linear regression. So the coefficients of linear regression will give us the feature importance. So I call it feature, and what do we need is feature dot columns, and let's call it importance. So this will be my whatever LR model we have. And if I remember, coefficients. Why does it take? If I remember, this is something. Wait. Let's check. Okay, we are getting this. What all methods we have? Oh, it's this coffee. Okay, it has an underscore here. Cool. Now we got this, and we need to sort them. Okay, now we will sort them with respect to their importance. Okay, and so weights can be negative also, because you are trying to fit a line. So it's something like you have this y, and whatever features you have some weight matrices for them. So summation of the wi and your features, okay, that will give you y. So this weight can be negative, right? So we need to, so whenever we are shorting, we need to consider the absolute value of this. So I need to consider, you can put absolute. So this will take all the absolute value, and let's sort them with ascending order. Okay, now once we have this, let's plot this value. So let's let's set the fixed size to be 20, 10. Okay, now we will be plotting a bar plot. So feature importance. So on X we will have feature, and on Y we will have the importance, like the coefficients. Importance. Okay. And since we have 79 features, so I guess good visualization will be rotation. But yeah, let's check how does it look. So let's just pull this X label. So on x-axis we have features, right? So this is features, and on y-axis we have this thing. Importance. Okay, so much importance. And title, linear regression based features importance, and then let's show it. And I guess I will be needing this x station, so by 90. Boom, we got a error. We got this error. Was it features? Got this. Oh yeah. Per column array must be one dimensional. Okay, we are getting this error, which let's check this. We got this right. Okay. Is this not getting created? Okay, so let's take the 0th value. Cool, and let's make the grid also. Okay, so what we can see is that there's a very heavy weightage is given to feature 25. Oh no, yeah, 25, then 61. So let's check out the result here. So here we got 6, 7, 64. Let's check whether they are there. 6, 7, 64. Okay, linear regression is saying there is no significance. And where do we have 7? 7 also. And 64 also, I guess. That is 64. Yeah, 64 also, very less significance. Okay. So linear regression is saying me this. Okay. So yeah, you can see. But yeah, we can consider mix of both worlds. Now, another idea will be to consider not just this, also let's consider the responders columns. Yes. And call dot starts not equal to my, let's put this here. So I'm basically saying, so let's consider the responders also. Okay. And then let's check the features plus responders. Okay. And let's try to fit this. Okay. So 3 and 5 are showing some. So 3 and 5 are matching with our Granger test. 7 also. Okay. But yeah, let's try to do only res. And let's put this somewhere here. So you will get call for this. And if this goes here, okay, or this. Okay, let's remove this condition. And then let's run only for responders. So 3 and 5 have significant impact. Okay. 7 being lower, 8 has a significant impact. Okay, let's check out the loss. Not markdown, I need code. Only considering responders, right? So R2 score for loss. Okay, so we have this ypred, so this will be lr model dot predict, and we have x test where ypred will be this. Then let's see np called squeeze, right? Y spread. So just converting them into a 1D vector. Cool. Now let's compute the weighted R2 score. Now for weighted R2 score, I need the weights. So basically with respect to the competition, how is it? Or there is one, but let's first plot that, plotting the predictions. Okay. So I need multi-line plots, right? So PLT figure, so figure size 26, and let's, do I have Seaborn? Let's import Seaborn also. Okay. I've done the same exercise with XGBoost, right? I should be able to figure it out. So SNS, but yeah, I'm still forgetting. No, I don't want this. I want line plots. SNS multi line plots. Is, oh yeah, so you just give X and Y, right? So SNS line plot. So we got Y spread. So Y X test. What is this? This is this, right? So let's check Y test. This is this. Okay, so I can use Y test index. I need this X Y spread and Y test dot values. Okay, is it showing me? Okay. X is this, Y is this. Somewhere here. Yes. Somewhere I remember you can give in stat form. All arrays must be of same length. What? Y spread dot 2000 values, then Y test index. ND array is not callable. Which one is ND array? Oh, okay. This one is ND array. Ah, okay. 2000, 2000, 2000. Okay, so everyone is 2000, right? Oh, because of this. Let's multi-line plot. Signal hue. Let's just create a data frame. So I did a frame. columns. This is y test, y spread, then data list zip, and first I will have y test dot values, and in next I will have y spread. Okay, now this should give me, so PLD title fitting of linear regression, then PLD dot show. I'm only getting y spread. So data is this. Uh, let's get this. Red DF as this. Red DF as this. Red DF index. How can I? Let's check. Hmm. Here goes multi-line. Usually I don't need to give this right. I simply do this. Ah, it's working. Oh, but why is it taking this? Ah, why test is appearing like this? That's why it is not appearing. Okay, so y test values can do d of 0 or d in this. Okay, cool. So you can see we are getting a very significant, so it's fitting really well. Okay, like there are some nuances, but it is fitting good, I can say. Let's compute the R2 score. So okay, RMSC, let's call it weighted RMSC. Let's check out that, and weighted R2 score. Let's just a sec. Cool. Uh, yeah, let's compute this. Weighted RMSC. So def weighted RMSC. So yeah, this fitting may look good, but here you can see like, as so if you guys haven't watched my XGBoost and Light GBM fitting, so please watch that. And there I have used k-fold cross validation. Okay, where I have kept the distribution of my training and validation set same. Here the distributions are not same, so it might happen like we may be doing good, but it's not that like, because it's just a sample. This sample may not be covering the whole data set. Okay, because I simply ran a simple train test split. I haven't done any stratification, anything. I haven't done. So based on the range of values, we are we may think like it's good, but if you observe like The training values are varying between minus, like the data set values were varying between -5 to 5, right? Here you can see like we have upper limit up to 4, right? 4 to like some 4.5, 4.75 to -4. Okay. So this is not a good representation of the overall data set that we have. It's just a part of the data set and we are fitting over that. So yeah, this thing like just to be on the same page so that watch like people who are watching this video may not think like, hey, we can try with linear regression and we can use this and simply uh, create an inference. So this is a small part of the data set. It may work. You guys are like feel free to do it, but yeah, I'm just saying it's just a small part of the overall data set. So we consider y pred and then we do y test. And similarly, we have weighted R2 score. We consider y weights, y pred, y test. Okay. Now for RMSA, it's pretty simple. So you have weights and you compute. So score is weights. So we weight the difference between y pred and y test, and we normalize them with, let's call it numerator, with the constant. So if I remember, this is the formula, right? W I y hat square upon, yeah, this is RMSE, and for R2 score you have weight of this and like similar thing. Yeah, for this competition they were squaring also, right? For evaluation, yeah, they were performing a squaring. So this is weighted R2 score, this is weighted RMSE. Yeah, just to be on the same page, let's just check. Weighted RMSE. Oh, if I remember, so sklearn has this, right? Sklearn, or yeah, let's implement it. Okay, we only consider weights here. Okay, so this part we do not consider. Okay, cool. So denominator, which is np dot sum of weights, and let's put epsilon also. So let's do 10 to the power 16. So we do numerator. So I put a epsilon just to avoid the zero division error. Okay, so this is weighted RMSE and weighted R2 score. So same thing, you have this as a numerator. For denominator, we are doing weights times the y test square, right? So this thing first, then weights, then we take the sum, then we take the epsilon, then we take numerator upon denominator. Yeah, cool. Once we have that, so let's call it val, and then we return 1 minus val. Okay, so we got our weighted R2 score and weighted RMSE. Okay, now here I need to consider, since I have given the seed here, I need to take the weight here. Okay, let's quickly consider the weights. So how can we, so train test split, does it give me, it has randomly given me these things. How can I figure out this thing? How can I figure, how can I figure this out? Do I have indices? Oh, cool. I have indices. If I do index, cool. So I can easily get the weights. I don't need this. I don't need this. Yeah, this is the plotting. Okay. So I need this thing. So weights is whatever my FDF have. So FDF my y test dot index. Okay. Boom. I got error. Uh, FDF equal dot index in what do you call equal to length lock. I got this. I need wait. Finally, cool. I got this weights. I have this. Now let's consider RMSC. So RMSC will be my weighted RMSC of my weights y spread, and I remember I need to do this, so let's quickly do this. Let's cut this YGT, let's call this, okay, and YGT will be this. This should bring me this. Now this is a 1D vector, and this thing, but this is not a numpy array. I can convert it back to a numpy array. I want to convert this into a numpy array so that I can use that all these operation, because these are acting as operators in numpy. Then I will pass YGT. Y pred I have, YGT I have, then same thing. R2 score, weighted RMSC, weighted R, cool. And do I have a print statement here? No, right? Yeah, so W R2 score. Okay. I need to do NP sum. Here also I have to do NP sum. Okay, so R2 score is very close to 1, which is good. Okay, and RMSC is also looking good. But yeah, since this is a part of the data set, I'm not quite sure like whether this is a good score, because this is just a sample, and this we are only getting by considering all the responders, but in our test set we do not have any responders. Okay, so let's check this with features. Okay, now what I can do is I can bring this code, and here this also, we got the feature importance here, this also here. Let's bring this up so that we don't need to do this again and again, and let's do this. Okay, now what I will be doing is I will be conducting 3 experiments. One is with features, another is with only responders, and another will be features plus responders. Okay, so for all of them I will be changing my feature calls. Okay, so Yeah. So feature calls, for feature calls in, let's consider only features. Okay, only feature, and this only contains the columns which are feature columns. So call for call in, um what do we call it? So fdf columns, for call in column, if call dot starts with feet. Okay, so this is one experiment. Then only responders, call for call in fdf columns if call uh not equal to my target call 0, and call dot starts with res. Okay, then the next thing will be the concatenation of these two, features and responders. So this thing plus this thing. Okay, cool. Dict, I will call items, so I will call xp name feature calls. So for experiment name in feature calls, then experiment name will contain the keys, and this will be the feature call. So now we can bring this feature calls here. Okay, we don't need that. Now this we got fdf feature scal xtrend ytrend. We will put a linear regression here. Then we will compute the feature importance. Now for labeling, let's put a this thing. So let's print the xp name here so that we will have idea about the which experiment this plot was. So we got the xp name here. Then we got xp name here also, so that we can run a quick comparison. Okay, so I got fitting, I got feature importance here, I got predictions here. Okay, now this is with respect to the feature xp name. So that's a cool thing about Python, like you can automate anything. Really cool. Cool. So we got this, and since we are seeding with the same value, so all of them, so there is no shuffling happening. So this is good. So feature scaled, let's go through again. Feature importance, we are plotting this. Then model predict this. Data frame, then we are plotting the line plot. And then we are plotting the score. Cool, this should work. Let's try. Okay, we got the feature importance, we got the only feature. So yeah, considering only feature, you can see the fitting is not that great. The R2 score is very less. Okay, so all these spikes here, we are not able to model it. Okay, now considering only responders, significant importance is given to responder 3 and 5. Okay, and the fitting is really good, like we are getting a R2 score of 0.8. Okay, then features and responders, let's look at that now. Yeah, when we are considering the responders and the feature, the R2 score, like there is a boost in R2 score when considering only responders. So there is a 0.04 boost here. Cool. So this is all for this video, guys. And yeah, last but not least, I wish you guys a very happy new year. So, welcome 2025. So, yeah, I hope you guys uh, learned something new in this video, and I was able to capture all the segments that you should see in a time series competition. So, yeah, just try experimenting with all the things that I have described and just implement your own ideas in this competition. So, only 13 days are left. So, just pack up your bags and just run experiments, model, and yeah, that's all, guys. Thanks for watching. Stay tuned to watch more videos.